Okay, so this video is about torque, which is covered in chapter 12-5 in the textbook. Okay, so here we're moving into angular dynamics. So remember, dynamics is about why things move. Angular kinematics was about how. Dynamics is about the why. Okay, so if you remember, right, we talked about Newton's laws, and for linear motion or translational motion, accelerations were caused by forces, right? So this was Newton's second law. The net force on an object is equal to its mass times its acceleration. Now, you could ask the question, well, is there something similar for rotational motion? So in other words, forces cause translational acceleration. What causes angular accelerations? So it's related to force, but there's a little bit more to it. Okay, so what we have, so angular acceleration is due to something called a torque. And since we like to use Greek letters for the angular quantities, we're going to use a Greek letter tau to stand for torque. Now, when it comes to torque, I like to remember that everything you need to know about torque you can get from just opening a door. Right, so doors, right, to open a door, you need to make it rotate, so you need to apply a torque. Okay, so torque, well, it depends on a force, right? So there has to be a push or a pull to open or close a door, but it also depends on the direction of the force and the distance from the line of action. So the line of action is just the line defined by the force. So to imagine you take your force vector, and you just extend it out in both directions. That defines your line of action, and it's the distance from the line of action to the axis of rotation that's important. Okay, so if we want to write this as an equation, so you can calculate torque as the perpendicular component of r times the applied force, or you could think of it as r times the perpendicular component of f, or, well, in the perpendicular component, you're going to pick out with a sine of this angle phi, and so you could think of it as r times f times the sine of the angle phi. So if you look at the little image over here from the textbook, so r is a vector pointing from your axis of rotation to where the force is applied. Now, so there's some angle in between those, phi, and so you can calculate the torque as r times f times sine phi. Or if you prefer, it's this sine phi is picking out the perpendicular component. So so if this is phi, then sine of f times the sine of phi is this perpendicular component of the force. Or if you prefer, this is also phi. So this r perp, so that's the perpendicular component of r, which is sometimes called the moment arm. So any way you slice it, you need to multiply r times f times the sine of this angle, phi. So unit-wise, well, r is a distance measured in meters, f is a force measured in newtons, so the SI units for torque are going to be newtons times meters. Yeah, notice I like to write it newtons times meters rather than meters times newtons, because if you write it as meters times newtons, it's sometimes easy to get confused whether it's a meter times a newton or whether it's a millinewton. Okay, so, and remember, so this moment arm, r perp, is the component of r perpendicular to f. And one thing you do be careful with directions for torque. So again, it's actually the right-hand rule. We'll do some examples of this in class, but basically if you take your right hand, point your fingers in the direction of r, and you bend your fingers in the direction of f, then your thumb gives the direction of the torque. But since we're only going to be looking at the axis of rotation that stays constant, you could also think of torque directions as clockwise versus counterclockwise, so positive and negative.